Hello friends, greetings of the day. Welcome back to our exclusive channel on design of mission elements. Through these video sessions, we'll be trying to understand how to analyze the mission components. In today's session, we'll try to understand how a crank will work or what are the different stresses developed in a crank when a load is applied. When I talk about a crank, it is similar to a kick rod of a bike. Let us understand what are the various stresses developed when we are kicking this rod of a bike. This kick rod is in turn connected to the crank of an engine, which is responsible for starting the bike. Now let us understand by taking a simple example. Let us consider this example. An overhand crank with a pin and shaft is subjected to a tangential load of 15 kilonewtons. We need to determine the diameter of the section at XX. So this section is here. The diameter of the section XX using the maximum shear stress theory. When I talk about maximum shear stress theory, we have already understood that there are two theories which we started using. One is called as maximum normal stress or principal stress theory, and another theory called as shear stress theory, tau maximum. So this numerical he is trying to ask to determine this diameter using maximum shear stress theory. Also he has mentioned that the crank is made of C60 carbon steel having a yield stress of 412 megapascals, and also he is asking us to take a factor of safety of 2, and he has also given a diagram, illustrative diagram with the dimensions how the crank is looking. Let us now start solving this numerical by writing down the given data. Let us now start analyzing this problem. It is clearly seen in the numerical that there is a load P which is applied on the crank, or indirectly there is a load P which is applied on this rod. This rod is in turn connected to this frame. Because of the load on this rod, this frame rotates, which in turn rotates the other shaft. We need to determine stress at this area. This has been given as section X. So the section in this case is circular cross section, which is shown here. Because of the load applied in this rod, we'll try to determine the effect on the other side at section X. Let us start solving this numerical by writing down. We can see the three-dimensional view of this crank. The load P is applied on this rod, and because of this load P, we need to determine the diameter at this section X. The material of this crank is given as C60 carbon steel, whose yield stress is given as 412 megapascals. Let us now start solving this numerical. In this numerical, The load applied, which is tangential in nature, is given as 15 kilonewtons. The yield stress for C60 carbon steel is given as 412 megapascals with a factor of safety of 2. So by using sigma y and FOS, we can determine the maximum stress or allowable stress as sigma y by FOS, which will be equal to 412 divided by 2, which will be 206 megapascals. From now onwards, we will be using 206 megapascals for solving this numerical. This crank is clearly subjected to bending as well as torsion. So the combined effect of bending and torsion can be determined by using these equations. Sigma maximum is equal to sigma b by 2 plus root of sigma b by 2 whole square plus tau square, where sigma b is the bending stress and tau is the torsion. Similarly, minimum principal stress can be obtained by this equation. The maximum shear stress can be obtained by the following equation. We will be approaching this problem by solving. First, we will try to solve bending equation by using formula sigma b is equal to mb by z. Later, we will be trying to solve and determine torsional shear stress by using tau is equal to mt by z naught. Later, by using the combined stresses, we will be trying to find the diameters. Let us start with finding the bending stress. The bending stress is given by the formula sigma b is equal to mb by z, where mb is called as bending moment. The bending moment can be obtained by using the equation force into perpendicular distance. Now in this case, what will be the perpendicular distance? Now try to see in this diagram, there are two different perpendicular distances. Now perpendicular to what exactly is the question? That perpendicular distance means that it is perpendicular to the cross section. The distance which is perpendicular to the cross section is 100 plus 25 plus 50. This is the distance which is exactly perpendicular to the cross section. That is what the bending distance says, perpendicular distance mean to say to us. Now 100 means from the section to the frame it is 100, and now the thickness of the frame is 25 mm, which is clearly given here. Now from the frame to the point of application of load it is 50 mm. Therefore we will be using the value of 100 plus 25 plus 50 mm to determine the perpendicular distance. I repeat, the perpendicular distance is nothing but the distance which is perpendicular to the cross section till to the point of application of load. Therefore, the load F is 15 into 10 power of 3 multiplied by the perpendicular distance, which is also otherwise known as eccentricity. Therefore, we will be obtaining the bending moment value as shown on the screen. Once we get the value of bending moment, after determining the value of bending moment, we will be trying to find the bending stress. Sigma b is equal to mb by z. Z for a circular shaft is given by pi dq by 32. By substituting the values of mb, we will be getting the bending stress in terms of d, because we need to find the diameter of the shaft. So we will be getting the value of sigma b in terms of d cube. Let us now find torsional stress because of this load 15 kilonewtons. The torsional stress tau is given by equation mt by z naught. In this case, mt is nothing but the force applied multiplied by the radius of rotation. It can be clearly seen from the diagram that the radius of rotation is 500 mm. It is the distance from the load P to the axis of rotation. This is the axis of rotation. Therefore, mt is equal to the load applied multiplied by 500, which will be getting the value of 7.5 into 10 power of 6 Newton mm. Using this torque or torsional moment, we'll be trying to find the torsional stress. Tau is equal to mt by z0. Z0 can be obtained from data handbook, whose equation is pi dq by 16. By substituting the value of torque in torsional equation, we'll be obtaining the torsional equation in terms of d cube. Let us now determine the combined effect of bending and torsional load. The bending stress in terms of d cube is given by the following equation. The torsional stress in terms of d cube is also given. Now let us use the maximum normal stress formula to determine the diameter, and later we'll also use the maximum shear stress formula as asked in the numerical, so that it will be easy for us to understand what will be the difference between maximum principal stress and maximum shear stress. We'll be using the following equation. Sigma maximum is equal to sigma b by 2 plus sigma b by 2 whole square under root plus tau square, where sigma b is nothing but the bending equation and tau is the torsional stress. By substituting the values, sigma maximum, as we have got 412 megapascals divided by 2, which amounts to 206 megapascals, and substituting the following equations of sigma b and tau, we'll be able to determine the value of d. In this case, the diameter obtained is 63.93 mm. This diameter is based on maximum principal stress theory. Let us also solve by considering maximum shear stress theory. The maximum shear stress theory is given by or represented by the following equation: under root sigma b by 2 whole square plus tau square. Now, how do we determine maximum shear stress value? The maximum shear stress will be always 0.5 times of the maximum normal stress. So in this case, the maximum normal stress is 206 megapascals, which is obtained by sigma y by FOS. And in this case, sigma y is given as 412 megapascals and FOS is given as 2 megapascals. That is how we have got 206 megapascals, and dividing this 206 by 2 or multiplied by 0.5 will be obtaining the value of tau maximum as 103 megapascals. We will be using 103 megapascals in this equation, and also we will be trying to substitute the value of sigma b and tau to determine the value of the diameter. So by using maximum shear stress equation, the diameter of the rod obtained is 73.24 mm. So considering both the values as per maximum shear stress theory and maximum normal stress theory, the maximum diameter of 73.24 mm will be selected for the crank. Let us analyze one more example of a crank subjected to inclined load. At this time, the crank is subjected to a load which is inclined at 30 degrees with respect to horizontal. Let us now analyze how exactly the stresses are distributed in this structure. So in this numerical, we need to determine the maximum normal and maximum shear stress at section AA. Once again, when I say section AA, it is somewhere here. Section AA for the crank shown in the figure. When a load of 10 kilonewtons is applied at the center of the crank pin. So this is a crank pin. At the center of the crank pin, a load of 10 kilonewtons, which is nothing but 10,000 newtons, is applied. But we can see from the diagram that the load is applied at an angle with respect to the horizontal. This is a three-dimensional visualization of the model. In this case, the load is applied at an angle. The angle is exactly at 30 degrees from the horizontal. Now let us understand how the force is applied. In this case, as the problem clearly specifies in the diagram, a load of 10 kilonewtons is applied at an angle of 30 degrees with respect to horizontal. The following data are given in the numerical. A load of 10 kilonewtons, the diameter of 75 mm. Now we can see in the diagram there are two diameters, one at the crank pin and one at the main rod at the section A. Now here for us in this numerical, since this cross section is at A, the diameter 75 is of more importance than the diameter 50 mm. 50 mm is been given only merely to distract our attention. So here the viewers need to be careful in choosing the diameter. In this case, the diameter is 75 mm. This numerical once again falls under the category of bending and torsion. And the following formula are used to determine the combined effect of bending and torsion. Sigma 1 denotes the maximum normal stress or sigma maximum, and tau maximum denotes the maximum shear stress. Let us now find the maximum normal stress and maximum shear stress by determining individually the bending stress and torsional stress. To solve this problem, since the load is inclined, the first step is to resolve the forces. Let us resolve these forces into two components. One is the horizontal component Fh and other one is called as vertical component Fv. Now the horizontal component Fh will be equal to F cos theta, because the angle is next to the horizontal component. Will be taking Fh is equal to F cos theta, nothing but 10 multiplied by cos theta, which is nothing but 8.66 kilonewtons. And Fv, the vertical component of the force, is given by Fv is equal to F sin theta, whose value is equal to 10 sin 30 degrees, which is 5 kilonewtons. Thus, we need to resolve the forces into horizontal as well as vertical components. Then in the next stage, let us understand the effect of individual component Fh as well as Fv. Fh is mainly responsible for torsion, because if you can understand, if we are holding the cross section at section A, at this section if we are holding the cross section and if we are giving a load of Fh, then because of Fh there are chances that the entire crank will rotate. At the same time, because of Fh there may be a bending which happens at section A. So the effect of Fh is to produce torsional stress as well as bending stress. But in case of Fe, if for suppose Fe alone is applied onto this crank, and since the Fe is exactly vertical onto the crank pin, the overall effect of Fe will be only bending stress, and because of the vertical component there may not be any rotation. So the effect of Fe is to create only bending stress. Let us now start determining bending stress and torsional stress individually. Let us start with bending stress. The bending stress is determined by using the equation sigma b is equal to mb by z, where mb is the combination of horizontal and vertical bending moments. Now let us understand how do we consider the bending moments. In this case, the horizontal component as well as the vertical component both are in mutually perpendicular directions. Since both the moments are mutually perpendicular directions, we will be using the equation which is shown in the screen, root of mbh whole square plus mbv whole square, to calculate the overall bending moment because of the horizontal as well as vertical load components. Here mbh denotes bending moment due to horizontal component and mbv denotes bending moment due to vertical component. The bending due to horizontal component is given by force Fh into perpendicular distance. Now in this case, the perpendicular distance, once again I repeat, for bending the perpendicular distance is nothing but the distance which is perpendicular to the cross section. In this case, if you see the diagram, the distance perpendicular to the cross section is 38 mm from cross section AA to the crank to the frame, and plus 25 mm the thickness of the frame, and once again the distance from the frame to the point of application of load. So the total distance is 38 plus 25 plus 25 mm. So we'll be trying to use the equation 8.66 into 10 power of 3, which is nothing but the value of Fh, multiplied by the distance 25 plus 25 plus 38 mm, which gives the value of bending moment due to horizontal load component. Let us also determine the bending moment due to vertical load component. In this case, this bending moment is also given by force vertical component Fe into perpendicular distance. Now the question comes, which will be the perpendicular distance? As we have discussed in the earlier slide, the perpendicular distance in case of bending stress will be always perpendicular to the cross section. So for this case also, the perpendicular distance will be 38 plus 25 plus 25 mm only. Viewers are requested not to get confused with 125 mm. This 125 mm is the distance between the axis of rotation and the load. So in this case, for bending moment, the perpendicular distance will be perpendicular to the cross section and also till the point of application of load. So in this case, Fv is 5 into 10 power of 3 newtons multiplied by the perpendicular distance, which gives the value of vertical component of bending moment. Now by using this vertical component of bending moment and horizontal component of bending moment, we will be trying to find the overall bending moment of the structure. We have got the value of mbh, we got the value of mbv. So by using the formula which has been already stated, we will be trying to find the overall bending moment. This bending moment can be used now to find the bending stress. There is another component which is very much required to find bending stress, that is section modulus, which is given by the equation pi d cube by 32. In this case, the diameter d has to be considered as 75 mm. It is not 50 mm, which we need to consider, because we are not trying to design the crank pin. We are trying to design the shaft at section AA. So the diameter is 75 mm. So by substituting the value of Z and bending moment, we will be determining the value of bending stress as 21.24 megapascals. Let us now determine the torsional shear stress in this crank. The torsional shear stress is mainly due to horizontal component and is given by the formula tau is equal to mt by z naught. In this case, mt is nothing but the twisting moment or torque, which can be obtained by multiplying the force with radius of rotation. In this case, the radius of rotation is nothing but the distance between the axis of rotation and the point of application of load. So in this case, the distance between the axis of rotation and the point of application of load, that is nothing but Fh, is 125 mm. So in this case, we'll be using the formula Fh multiplied by 125 mm, which gives the value of the twisting moment. By using the value of torque, we can also determine the torsional shear stress. Before finding the torsional shear stress, it is important for us to determine the section modulus or polar section modulus. The polar section modulus is obtained from data handbook from from table number 2.2, and it is given by the equation pi dq by 16. So substituting the values of twisting moment and polar section modulus, will be able to determine the torsional stress, which is 13.068 megapascals. Now let us determine the combined stresses. The combined stresses, because of bending stress, which having a value of 21.24 megapascals, and the torsional stress 13.068 megapascals, can be determined by using maximum principal or normal stress theory, which is given by the equation sigma maximum is equal to sigma b by 2 plus root of sigma b by 2 whole square plus tau square. By substituting the values of sigma b and tau in this equation, we will be able to determine the maximum normal stress, whose value is 27.459 megapascals. The maximum shear stress can be determined by using the following equation. By substituting the values of sigma b and tau in this equation, we will be able to determine the maximum shear stress, whose value is 16.839 megapascals. The viewers are requested to try to determine the maximum normal stress and maximum shear stress for this example shown in this diagram by using the knowledge obtained in the previous examples, so that once we practice it, you will be more comfortable in determining and understanding the stresses developed in the crankshaft because of the load applied at the crank pin. Thank you friends for watching this session. Make use of this session and start practicing the numericals. We'll be meeting in the next session with some more new numericals. Till then, have a nice day.